Homework Solution 6.3. For the given 1 to 2 ideal transformer circuit, find the current in the primary, the voltage across the secondary, and current in the secondary. And then we've been given this circuit. So the givens really is the circuit. Don't really have to draw anything other than the fact that we're going to indicate that's a 1 to 2 transformer. It's a step-up transformer. And we are asked to find current in the primary, which is I sub P, voltage across the secondary, V sub S, and current in the secondary, I sub S. So there are a couple methods that you can use, two methods that you can use to solve this circuit. One is to set up a system of equations for the primary and the secondary, and then relate primary and secondary current and voltages through the turns ratio of the transformer. That's the hard way, and not the way that you should be doing this in this class. You should be using the technique of reflected impedance, especially when circuits get more difficult than this simple ideal transformer. The technique of reflected impedance is the one you're going to want to use. Primary way power analysis is done involving transformers or any other subdiscipline that uses transformers like audio or such things. So the technique here is that what we have is some sort of impedance connected to the primary circuit, and then we have the primary voltage across the transformer. We've got some sort of load impedance connected to the secondary right here, and we know that there is a turns ratio, in this case 1 to 2, and that's the secondary. And then we've got two currents. We've got the primary current and we've got the secondary current. And what we want to do is we want to simplify this circuit such that it looks like this. We've got a primary side input. We're going to get rid of the transformer completely, and we're going to replace it with the load ZL prime. And what we've got right here is the voltage of the primary, plus, minus, and we've got the current through the primary. So this is called referring the impedance to the primary, or reflecting the impedance through the transformer to the primary. So what we need to do is we need to figure out, well, what's ZL prime? ZL prime is the turns ratio squared times ZL. So we've already done an example where we related the voltage and currents to one another in the primary and secondary side via the turns ratio. Now we're seeing that you can actually relate impedances across the transformer by using the square of the turns ratio. So you have to remember that squared term if you're working with impedances. So to determine this, ZL prime, we just need to know what the turns ratio is, 1 to 2. So we square that, and then we multiply by ZL, which was just 2 minus J2 plus 2. So ZL prime in this case is going to be 1 minus J 0.5 ohms. So the circuit that we're going to analyze just looks like this. 12 at angle 0. We've got a 2 ohm resistor, a 2 ohm cap. We then have, let's see, that's 2 plus 2 is, oh, no, referred, 1 minus J.5, sorry. So that's the circuit we have to analyze. Fairly straightforward. This remains IP, so the current in the primary is going to be equal to the voltage source divided by Z total, where that's the total impedance of the series branch. So that's going to be equal to 12 at angle 0 degrees divided by 2 minus J2 plus 1 minus J 0.5. So we get 12 at angle 0 degrees divided by 3 minus J2.5. So that gives me a voltage, or a current rather, of 3.073 at an angle of 39.81 degrees amps flowing in the primary side. Can real easily determine secondary current using the turns ratio. NP over NS times IP. Remember, the primary current is divided by the secondary current is the inverse of the turns ratio. So that's going to be equal to NP. Remember, this is a 1 to 2 transformer. So step up, so that's 1/2 times the value we just calculated for I sub P. So we get 1.536 at an angle of 39.81 degrees amps. We see that in a step-up transformer, the current in the primary side is higher than the current in the secondary side. So that's looking good right there. So we want to determine VP. Looking at this diagram, if I take IP and I multiply it by ZL prime, I get VP here. So VP is going to be equal to IP ZL prime. So that is going to be 3.073 angle 39.81 degrees amps times ZL. I forgot my prime there. ZL prime 1 minus J.5. So let me just make sure that's right. Primary current, reflected impedance 1 minus J.05. Yep, looks good. So I get a primary voltage of 6.872 at an angle of 13.24 degrees. So if we go back to the original diagram, that's the voltage from here to here. It's reduced due to the current flow through whatever was connected between the voltage source and the ideal transformer. Guess I should indicate that that's volts. And so then I can get the secondary NP over NS equals VP over VS. So I can determine secondary voltage VS is equal to VP times NS over NP. So this is going to be equal to NS was 2. I think I've made a mistake here. Hold on a second. I did make a mistake. Hopefully you guys caught my math error right there. That is not 6.872. It's 3.436. 3.436, so half that value. Something didn't look right there. So my apologies. So anyway, I need to take the VP, and I need to multiply it by 2 to 1 in this case, because this was a step up, so NS is larger than NP. So that is going to be 3.436 at an angle of 13.24 times 2 over 1. That's going to give me 6.872 at an angle of 13.24 degrees volts. So that would have worked. The other way to determine that was, so basically in this method I calculated the primary coil voltage and used the turns ratio to calculate the secondary voltage. Another way to do it is if I know the secondary coil or secondary current, I'll just multiply it by the secondary load. So IS times ZL, where ZL was 2 minus J2 plus 2. So I could have said, I'll just do an OR. V secondary is equal to I secondary times the load connected to the secondary side. We calculated IS as 1.536 at an angle of 39.81 degrees. ZL was 4 minus J2. It was 2 minus J2 plus 2, or 4 minus J2, and we get a value of 6.872 at an angle of 13.24 degrees volts. So the reason I did this is because I just want to illustrate there isn't one method to solving transformer circuits. The key is to recognize what you can refer back and forth, which is voltages, currents, and impedances. And if you're referring voltages and currents, you need to use the turns ratio. And if you're referring impedances, you need to use the turns ratio squared. So that's important to distinguish the two.